associate professor in the math department there, who has been doing a lot of work, both at UC Berkeley and I guess at LBNL and with collaborators there in computational quantum chemistry and electronic structure calculations. Lin is one of the people that got me into this area, so I can say, I've learned a lot from Lin over the years. I'm very happy to have the opportunity to give this talk on Grassmann manifolds, gauges, and quantum chemistries. Lin?
Okay, thank you. Thank you, Neil, for the invitation. It's my first time at Cornell. It's a great pleasure to be here and have a very nice visit so far. So today I'm going to talk about some recent work that I've been doing on this topic. I know that most of you, some of you might have heard about Grassmann manifold, fewer have heard about gauge or quantum chemistry, but I'll do an introduction for those things are. So just to start from something basic, so there's something called a Stiefel manifold, and if you don't know, it doesn't matter at all. It's nothing but a matrix, and size is 5n, and it's much larger than n, so it's a 4-stage matrix. So it comes from Stiefel, 1930s, and so basically n orthogonal vectors in Cn. So each vector is of size n, put them together, and it needs to be orthogonal in the sense that x star is a star means that permutation and conjugation, x star x, so this should be a square matrix of size n by n, and the collection of all these n orthogonal vectors we are called the Stiefel manifold. What is a Grassmann manifold? It dates back to Grassmann earlier in the 19th century, but its importance wasn't recognized until the 20th century. And that thing is basically the set of the n-dimensional subspace in Cn. It is obviously very closely related to the Stiefel manifold because I can just choose any n vectors that are orthogonal. That would be a legitimate basis for a subspace, n-dimensional subspace. But there is something different when you look at the subspace. This is because when we talk about subspace, you don't actually care about a particular representation. You can choose a basis, but you don't care which basis. So I can choose a basis and then apply a unitary rotation because everything is complex. And I can do a unitary rotation of size n by n, and any of this rotation would be equally good. So I take a basis, I can define an equivalence relation among n vectors and n vectors. If they only differ by n by n rotation, you can think they are equivalent. So by defining this equivalent relation, you can formally write it down as the quotient space of the Stiefel manifold over the unitary n-dimensional unitary group, and the resulting thing is called the Grassmann manifold. So it's nothing but n-dimensional subspace. So in particular, any point in the Stiefel manifold can be viewed as a representation of a point in the Grassmann manifold, but it's not the only representation. So give an example, in optimization, you're trying to minimize a function called fx subject to the orthogonality condition. Sometimes a function is special in the sense that it doesn't matter how you rotate this thing. And when fx equals fxu, u is in un, for any x and u, then it means that this function and this optimization problem is invariant to the choice of the basis. That means you're doing optimization on the Grassmann manifold. And in this case, this representation u, you can be lazy and choose it to be identity, but that's still a choice. So this representation u is immaterial to the optimizer and the value of the optimization, and it's called a gauge in quantum physics and quantum chemistry. So let me say it again. A gauge is something that you have to choose to do computation. Sometimes you don't realize that you're choosing that because it's an identity, but it still is a choice. You choose that to do computation, but it has nothing to do with the actual value of the computational problem. And when this is satisfied, the problem is called gauge invariant. Otherwise, if the result does depend on that rotation, it is called gauge dependent. So there's a seminal paper by Adam and Arias here, and Smith in 1998, and which describes the basic procedure of first order and the second order numerical methods, and on optimization of the Grassmann manifold and the Stiefel manifold, and many works that follows this direction. So this talk is about quantum chemistry. In particular, I intend to talk about three topics. One is time-dependent density functional theory, TDDFT. The other is ground state Kohn-Sham density functional theory, called the Kohn-Sham DFT. And the third one is localization. In all the three things, the gauge choice is the key, but I know that from my previous experience, I probably wouldn't be able to finish everything. So I'll try my best to talk about the first two. The third thing is joined with Anil here, and he's a local expert, and you can just consult him for the thing on the localization. But just to let you know that it's not just some sort of abstract formulation, it actually leads to useful numerical algorithms that, although these things have all been developed relatively recently, they are already used in community software packages, such as Quantum Espresso, 190, Alpha, DFT, so on and so forth. So they are really useful for actual computation. I'll spend most of the time of this talk, not all of that, on this topic, which is a recent thing on time-dependent density functional theory, and the new technique we developed is called the parallel transport gauge. So TDDFT, from a more abstract perspective, so it was developed by Lin and Grass in 1980s, and what it basically tried to say is the dynamics of n electrons that are interacting with each other under an external field. So that's a lot of terminologies to expand. Let me say what is mathematically, what it is doing mathematically. You have NE electrons, and that are interacting with each other. So they are discretized by, described by NE fields or functions, psi I, x, t. Each x is a low-dimensional thing, let's say in R3, and you can also discretize that. And you have each electron is described by a function and psi I. That's not the precise way of saying that, because the electrons are identical particles, and there is a way to put them together using Slater determinants. I won't go into that. But just keep in mind that when you have 1,000 electrons, you actually have 1,000 of these fields. This is the Schrödinger equation, I partial t psi I equals to a Hamiltonian operator that depends explicitly on t and implicitly on t as well, on something called p, which I'm going to explain. H is a self-adjoint operator applied to psi I, and at each time t, and you propagate. Pt is the central object that is going to be talked about throughout the talk, defined to be an integral operator with this kernel being pxx prime t equals to summation I from 1 to the number of electrons, psi I xt, psi I conjugate x prime t. So you're going to see this later. This is called a density matrix. This Hamiltonian takes the form, so there's the 1/2 Laplacian, this is called the kinetic energy. V external t could be, for example, laser from an external field, and this is called the external potential. And this part characterizes the electron-electron interaction called the Hartree exchange correlation term, which is the characteristic term in the density function theory. It depends on Pt rather than the individual psi i's. This is important. Its exact form can be complicated, but it's immaterial to the talk. So just remember it depends on Pt, that would be good enough. Just to give you some idea of what this kind of computation can do, let me show you a very small example calculated using our code. So this is a very small molecule, CH4, and what you're seeing is that under the external laser field along the x direction, so this means the laser field gets higher and higher in terms of the magnitude, And it is able to excite the electrons from the ground state to some excited states. How do you see that? What you're seeing here is the difference of the electron density at the time t compared to the ground state. At the beginning, you see that it is just some minor oscillation around the ground state, but after, you can see after this time here, there's some real excitation. The nature of the orbitals becomes different, and these are the p-like waves. And after the laser field, you can see that definitely becomes more complicated. Along the way, you can measure the difference of the electron density and to obtain other physical observables, such as the dipoles and many other things. Those can be compared with the real experiments. So these are really what people in computational quantum chemistry and computational material science do and compare with the experiments in a light source or something. So just to let you know that this is not just some formalism, but that people actually do this type of calculations on a daily basis. So the key quantity throughout the talk is going to be something related to the gauge. And a quantity is called the density matrix. To be clear, although before I said all this psi I from 1 to NE, those are fields, but to do computation, you have to discretize it first. Without loss of generality, then you be lazy and discretize each field using NG grid points. So NG means number of grid points. So there are NE of those things. So NG plays the role of M, as you see, as you saw earlier on the first slide. NE plays the role of N, and NG, the number of grid points, is going to be much, much larger than the number of electrons. So these form a tall, skinny matrix. If you compare the previous slide, the definition of the density matrix, you realize that P can be written in the way that is an outer product. So that's the density matrix. More specifically, P is a matrix of size Ng by Ng. It's a very large matrix. It is exactly a low rank matrix with rank Ne. So this is Ng by Ne and Ne by Ng. So it's a density matrix. So it is gauge invariant in the following sense. Assume I do a unitary rotation of the wave functions, psi, and U is an Ne by Ne unitary matrix satisfying this condition. Then you just define P to be phi phi star equals to psi U U star, and which is equal to U star U equals to identity equals to psi phi star. So it means that this P does not change when you apply this unitary rotation. That means I pick any representation in the subspace spanned by psi, it will give me the same density matrix. This is not surprising at all because P is nothing but a spectral projector associated with the subspace, and which is uniquely defined from the subspace, right? So you might say, okay, why don't you, since you have something that is gauge independent, which for the rest of the talk we'll call it to be physical. As a matter of fact, this really defines what is physical. So something physical means you can measure. And a gauge, if something that is gauge dependent, you cannot measure. Let's say in electromagnetic theory, you can measure the magnetic field B, but you cannot measure the vector potential A, for which the relation is the curl of A equals to B. So there is a gauge, it's not physically observable. Similarly, you can measure P, and this is derived quantities such as this diagonal, called the electron density, the integration of the electron density with some other things called the dipole, so on and so forth. But you cannot measure psi because there is this gauge in there. Does it make sense? Okay. So you say, okay, why don't you directly propagate the thing that is gauge invariant? This is indeed very known, called the von Neumann equation, or the quantum Liouville equation. It only takes a line to derive. So I partial t pt, remember p is psi psi star, you apply psi t, partial t to here and partial t to here respectively, you will end up with the commutator of h and p defined to be h times p minus p times h. So the equation is known, and people do evaluate, do the computation using this von Neumann equation. Why do we still bother? Because although the Schrödinger equation and the von Neumann equation are mathematically equivalent, we also want to know whether they are numerically equivalent or not. Let me show you with an extremely simple example that they are not numerically equivalent. Let's consider a very boring Hamiltonian, ht equals to h naught, which is a fixed matrix. Let me make it even more boring, that the initial state is psi I0, which is an eigenstate. And if you have learned quantum mechanics 1, or just to do it by one-line calculation, you will find the exact solution, which is psi it equals to the initial vector with a rotating face. So that's why it is boring, because nothing is going on. However, from a numerical perspective, because there is a rotating face, it means that using any numerical scheme, unless I know exactly it is rotating like that, I need to use a relatively small time step to resolve this rotation. However, if you look at the density matrix, again, you will find h and p commute at all time. So the right-hand side remains to be 0 at all time, therefore pt equals to p0. Which means that formally, you can take an arbitrary time step, because the right-hand side is always 0, no matter how you add, it's still 0, no matter how crappy the numerical scheme is. So you can take a formally arbitrarily large time step, that should be still fine. So that shows, even with this extremely boring case, the two things, although they are mathematically equivalent, but in practice they are not. As a matter of fact, yes?
So you've argued that for time-dependent problems,
right,
it's much more efficient to use the density matrix.
I'm not saying that yet, because efficient can be viewed from the temporal perspective. There is also the spatial perspective.
That was my
Yeah, I'll definitely go to that. So I've heard in more than one case that there's actually a two-scale problem from physicists about this TDDFT problem. So there's one scale, which is the so-called physical observables: density matrix, electron density, dipole, so on and so forth. Those things happen in the sub-femtosecond time scale. So a femtosecond is 10 to the minus 15 seconds. Sounds like very small, but it's really the time scale where atoms jiggle around. But the wave functions, psi, they live in the sub-attosecond time scale. An attosecond is 10 to the minus 18 seconds, so which is about 2 to 3 order of magnitude smaller than the time scale of the physical observables. So there actually has been a recurring question that whether you can actually develop some sort of a two-scale or multi-scale integrators that actually take advantage of this scale separation. The rest of the talk, I hope I can convince you that this two-scale problem doesn't exist. And in fact, these two scales are completely equivalent, and the only difference is due to the gauge. And as a matter of fact, you can completely eliminate this time scale separation problem by choosing a proper gauge. So let me see. Going back to Cyrus's question, that's an excellent question, which means actually more generally, the choice of a P versus the choice of psi is a recurring theme in many of the quantum physics, quantum chemistry calculations. In this particular context, the propagation of P requires storing a matrix of size ng by ng. It is often impractical to even store the matrix if you use a so-called large basis set such as finite differences and plane waves. This is because the size of the matrix is often on the order of 10 to the 3 to 10 to the 6 or 10 to the 7. Let's say if a million by million matrix, store that even with a supercomputer can be rather challenging. on the other hand, the propagation of the wave function can be much more practical, because NE can be on the order of 10 to a few thousands. So you are storing a matrix of size NG by NE, which even when NG is emitting is actually quite doable. So, however, we also know that P is only a matrix of rank NE, so it's really not that much justified to store P as a dense matrix. But it's not that easy either to just propagate, let's say we do a low rank decomposition, because the moment you do a low rank decomposition, you have to choose a gauge. So it's a chicken and egg problem. So, right? So, I mean, the whole point is to get around the gauge when doing the P. So this choice between P and the psi, as I said, is a common theme in quantum chemistry calculations. So the Schrödinger gauge, or the Schrödinger equation, can be viewed as a particular choice of the gauge. It is so common that you forgot that there's actually a gauge, because you actually choose the transformed orbital, and at every time t, you choose the gauge to be identity. And you might wonder whether we can do a little better than that. You might wonder whether we can actually choose the optimal gauge at each time step, so that the gauge transformed orbital for phi t to move as slow as possible without altering the physical observables, which is the density matrix. So this becomes a problem that is optimization on the Grassmann manifold. You might wonder whether it pays off to do that at all. I mean, it sounds complicated. You optimize it each time step. Why don't you just close your eyes and propagate? This is indeed what has been done so far. But, well, it still makes sense to ask the question. And I have to point out that there's a very related work, but from a more general perspective, try to do this, address this gauge issue, but from a more general perspective, called the dynamical low-rank decomposition. Started by Lubitsch and collaborators about more than 10 years ago, but there's an important difference from what we do and what they do. If you're interested, and I'll be more than happy to talk about the differences after the talk. So what we want to do is to do the gauge transformed orbital, or wave functions. Phi t equals to psi t ut, and ut, instead of being identity, is just constrained to be a unitary matrix. The goal is to yield a dynamics that is as slow as possible, which means that I want to minimize the derivative of the wave function under some norm. In this case, I choose the Frobenius norm because the Frobenius norm is easy to do linear algebra. So you can choose other norms, it's just more difficult. There needs to be some constraint, that is, this phi t should still span the same subspace as that spanned by psi t. And you can also rewrite this equivalently as pt as a projection operator applied to this orthogonal matrix is still the same set of orthogonal matrix. And it's orthogonal, and you can see that it's the same thing. So this implies the span of that, the projector corresponding to the span of this must be pt. So it's the same thing. And you want to do this at every time t. Okay? Let's do that. The first step is just a one line. So there's an orthogonal decomposition thanks to the inner product structure induced by the Frobenius norm. The phi dot Frobenius norm squared equals the p applied to phi dot plus the orthogonal part I minus p applied to phi dot. Now let me compute the second part first. After some derivation, you will find this one equals trace p dot squared p. The exact formulation doesn't matter. What matters is that it only depends on p. Remember, we're optimizing with respect to gauge, which means that whatever optimization we do couldn't change physical observable. And p is the physical observable. So if a term that only depends on p, no matter how complicated, how fast, those things those has nothing to do with the gauge. You just live with it. So the best hope to minimize this thing would be to take this term to be 0. If you can do that, then you have guaranteed proof this is the slowest dynamics. The optimizer satisfying this condition turns out to be unique, and this is the so-called parallel transport condition. If you know a bit more about parallel transport operator, you will actually see that this is a theorem that this induces a parallel transport propagator, P, in the following sense. P, assume it is known on a finite interval from 0 to some capital T, then it induces a parallel transport propagator using this self-adjoint operator. It's a weird operator which is the commutator of I partial T and P. This one is actually self-adjoint. And it defines a unitary evolution operator T. And you can prove the phi T satisfying this equation would exactly be given by this T, this operator, transporting the initial condition 2 times T. So this is indeed the corresponding parallel transport operator. You say, wait a minute, your original goal was to find a gauge. Where is the gauge? That's a very good question. So actually, we're not explicitly computing the gauge. If you directly compute the gauge, it's actually pretty complicated. But the gauge, the optimal gauge, is implicitly defined by the gauge transformed orbital phi. What I'm arguing is that it is actually easier to directly find this optimal phi, and the gauge is implied from phi. And you can just do an inner product phi transpose psi to get the gauge if you really want it, but this is completely useless. More specifically, you can derive a set of so-called parallel transport dynamics. Once you see the equation, it becomes so trivial that you see, it must be the case. Why? Because the Schrodinger dynamics says I partial T psi equals to H psi. And the parallel transport dynamics is a tiny modification to the Schrodinger dynamics in the sense that if you only add this extra mixing term, that is phi times phi star H phi. If you have learned an iterative method for solving eigenvalue problem, you will realize the term must look like that. Because if you forget about the left-hand side, and you were trying to find the block eigenvectors corresponding to this matrix H, and assume H is a fixed matrix, and when you solve the really least step, and when you compute the residual, what's that? It's exactly this thing. So instead of being propagated by the matrix vector multiplication, which we actually take for granted when propagating the Schrodinger dynamics, the parallel transport dynamics says the right way of doing propagation is actually to propagate based on the residual, which of course can be smaller. So as I said, there are a few features. The gauge is implicitly defined through the dynamics. There's only one additional mixing terms needed. This is extremely simple to implement. This is provably the optimal gauge among all possible choices of the gauge. And you do need to pay a little bit extra cost to compute this mixing term, but it is quite small compared to many other terms you have to do anyway in your PVDFT calculation. Let's go back to the previous boring example that you have this Hamiltonian HT equals H naught, and you can directly find the parallel transport dynamics. The right-hand side is also 0, and therefore you can also take an arbitrary large time step. In retrospect, this is very simple, because remember what was the problem that what was the problematic term in the original Schrodinger dynamics? It's the phase. What's the optimal gauge? Remember, gauge is a unitary matrix. In this case, it becomes a diagonal matrix. What's the optimal gauge? Just to get rid of it. That would be the gauge. If you enter I epsilon it multiply to that, and then you're done. So therefore the phi would be always equal to this in the parallel transport dynamics. Of course, if this is the only thing that parallel transport dynamics can do, it will be very much useless. I mean, nobody cares about that dynamics. Let me give you a more non-trivial but still toy problem. 1D time-dependent Schrodinger equation for which the exact solution does not exist. This black one would be the real part of the wave function along the time from t to be 100, and this is from the Schrodinger dynamics. The green one are the dynamics from the parallel transport dynamics. None of them is physical observable because it depends on the gauge. You have to measure some physical quantities, such as dipole. So the dipole you can compare with the RK full, which is fourth order Runge-Kutta method, used to do the benchmark. Use a very small time step, 0.005. Actually, because of the limitation of the stability condition, you will find that for this example, you cannot make the delta t to be much larger. So, but also it's accurate enough. Now, let's say, why don't we use some implicit time integrator, okay, to make the time step much larger? Let's say Crank-Nicolson. We learned that for linear problem, Crank-Nicolson is absolutely stable and unconditionally stable. That should be fine. That would be okay if the dynamics is dissipative and the corresponding equation is called the stiff. Let's recall what is the definition of a stiff equation. It not only says the equation you have to use a very small time step because of the stability constraint, it must also say that stability is the only constraint and you are not constrained by the accuracy. This is a characteristic example of the dissipative equations, and although the dynamics is very smooth, you have to take a very small time step. No, for highly oscillatory dynamics, for example, Schrodinger dynamics. Schrodinger dynamics are highly oscillatory. All the eigenvalues are along the imaginary axis, so you are simultaneously limited by stability and by accuracy. This is, if you haven't seen this before, this is a perfect example for showing that. You can indeed use the Schrodinger gauge Crank-Nicolson, use a time step that is almost 100 times larger, that the dynamics didn't explode after 10 t equals to 100. If you use RK4 by t equals to 100, you are 10 to the 300 or something. So it has blown up long before. However, if you look at the result, the red one actually deviates significantly. At the beginning it's okay. Afterwards, it dephases compared to the reference solution. This is because you can improve the time step, but they lose accuracy. So you are bounded actually by accuracy. However, as I said, if you use the parallel transport dynamics, the dynamics becomes slower. You can see I can use a time step that is almost 100 times larger, and it almost exactly tracks the dynamics all the way to t equals to 100. Why this is the case? This is because a Crank-Nicolson scheme, although it can be unconditionally stable, it is nothing but drawing a straight line. And if the trajectory looks like a bunch of circles going around, and you draw a straight line, even though it is stable, it doesn't look like a very good idea. However, what the parallel transport dynamics is doing is to sort of locally straighten it up into a much closer to be a real line, a line. So you can think, if I draw a straight line here, it's actually okay, but that would be a terrible approximation to that. So if locally it looks like this, you can see a straight line becomes a much better approximation. So that is why the accuracy becomes better, and significantly better in this case. And what I want to advocate is the use of implicit time integrators is really crucial. So, I mean, the parallel transport dynamics is a dynamics, can discretize with any integrator. But if you use explicit integrator, it won't work. Because in TT-DFT, the spectral radius h is usually large. And h times delta t for reasonable delta t, especially the sub-femtosecond, it is much bigger than 1. So any explicit integrator will blow up if this one is much bigger than 1. So you have to use implicit time integrators. But the people before, even up to 2018, there was a comprehensive paper published on JCTC by Angel Rubio's group, and which is a very well established group in this business, and compared all sorts of numerical integrators. Actually, at that time, I was teaching in Berkeley a course on numerical solutions to differential equations, and so all the A, B, A, M, all sorts of schemes. And while teaching that, I saw this paper online, which includes almost everything I taught in the class together with something I didn't teach in the class. And the gist of that comparison is implicit time integrators is not competitive. Why? Implicit integrators require you to solve a set of self-consistent equations, which has its overhead. However, if you cannot really increase the time step while keeping the accuracy, why do you want to go for the implicit? However, what I want to say is, at least in some cases, this is because of the wrong choice of the gauge due to the Schrödinger dynamics. If you choose the right gauge, actually you can use implicit integrator. So, this is because the dynamics is smoother. So, for example, in the parallel transport Craig-Nicholson, this is just a tiny modification with this mixing term, which you have to do fixed point iteration anyway in the TDDFT because of nonlinearity. It is very natural to combine with the motions of the nuclei, the so-called Ehrenfest dynamics, and many other numerical schemes are of course possible to combine. You might ask at this point, does parallel transport gauge, is it always beneficial to use the parallel transport gauge? And if it is, when would you expect it to be most beneficial? So the answer to the first question is almost always yes. And because you don't lose anything, you're just changing the gauge. So the second question is trickier, which is, what's the condition for this to be really beneficial? So we want to do some analysis. And let's see, from intuitive perspective, what we want to see is the dynamics is smooth, which means the right-hand side of the equation should be small, which further means that this residual, if you think about there's only one field, should be much smaller than the size of the matrix vector multiplication. When would that happen? That would happen when phi at each time t is close to be an eigenfunction. And this, in the quantum physics, is called the near adiabatic regime. I want to stress that near adiabatic doesn't mean perturbative. These two are completely different things. You can really go from one Hamiltonian to a completely different Hamiltonian, and just when you go smoothly from one place to the other. And this is actually the foundation of the so-called quantum annealer in the case of quantum computing going on right now, at least a branch of the study. But if you stay in this near adiabatic regime, we can expect this is much smaller. Mathematically, this corresponds to the singularly perturbed regime. We artificially introduce epsilon. In the real example, epsilon will be given by the physics. And epsilon is much smaller than 1. And you have this thing here. And what you can prove is the following. If you use the proper integrator, which is a symplectic integrator of order k, then up to t equals to order 1. In this case, it's actually a long time. What is short time? Short time means that you are on the order of t equals to order epsilon. You should propagate for a finite number of steps. And if you remember the error analysis of Euler or other schemes, and they're growing exponentially, so you cannot go beyond order epsilon time. But you want to go to t equals to order 1. That means you must effectively have some sort of a control of the long time error growth. And that is why you need a symplectic integrator. What you can show is, under some technical conditions, the error
from the shorter gauge would go like delta t to the k, coming from the accuracy, divided by a pre-constant, that is epsilon to the k plus 1. But if you use the parallel transport, the accuracy is improved by 1 order of epsilon. That 1 order of epsilon is what you have observed before. So the proof is based on a refined version of a quantum adiabatic theorem. Quantum adiabatic theorem, if you know, is basically saying that in the near adiabatic regime, the projector stays close to the projector to the ground state at each time t. But that's not good enough, because that just says the gauge invariant version, which is the projector, is close to a projector to the ground state. When you talk about the dynamics, we not only need to know the gauge invariant part, we also need to explicitly know the gauge dependent part. So what we proved is a lemma that is a refined version of a quantum adiabatic theorem, saying that this orbital from the parallel transport dynamics can be decomposed into a part that is smooth, or including the phase, and that is stays at the eigenstate of ht and is epsilon independent, including the phase, and the other part is epsilon times a residual part, and the residual part is bounded. This is the key for understanding this extra order of epsilon. If you look at the standard shorter gauge, you will also have this part, but there will be a phase that is epsilon dependent. Let me show this one, as I said, is implemented in our homebrew package called PWDFT, which is a self-contained modular of discontinuous scalar in DFT. It's in the process of being integrated into Octopus, which is the most widely used package for TDDFT. Give you a few examples for real molecules. First is atrazine, C14H10. We compare the real-time TDDFT with a completely different package called quantum espresso with a completely different method called the linear response rather than real-time propagation. So you can already see that for this, by the way, this is almost the worst case example, because the so-called absorption spectrum basically means that you do a delta kick to the initial orbitals that simultaneously excites all the wave functions, I mean among the all the waves, with a short and large time scale, and they will interact with each other. So the time step you can gain compared to RT4 is about the order magnitude, and the parallel transport is remarkably for the small system is already 8 times faster than the RT4. And they agree very well on the methods by the standard of this field, especially given this is totally different methods. And this is, as I said, it's like the worst case when you excite everything that is already kind of far away from the analysis we did for the near adiabatic regime. Let's look at the adiabatic regime. This is the so-called ultra-fast dynamics. And it's very much related to the so-called pump probe experiment, which is you shine a light on the material, it's called a pump phase, and then after that you do a probe laser and you probe the properties of the response of a molecule or materials. So this is a relatively slow laser, but still very much relevant to the ultra-fast dynamics. The span of the laser is about 10 femtosecond, and the parallel transport Craig-Nixon, in this case, can be used a time step that is 100 times larger, and that can be used by Craig-Nixon, RT4. This is sub-femtosecond, which is a 0.5 attosecond, and we're using 0.05 femtosecond, which is a 50 attosecond, 100 times larger. And this is the dipole along the x direction, along with the excitation. You can see that it breathes very well, and this is the energy difference. I can also use a larger, faster laser. You can expect I have to shrink my time step, and also the error gets a little bit worse. Indeed, you have to, but still you can use a time step which is 20 times larger, and but still it's about 10 times faster than SRT4, and the agreement of the physical observables with SRT4 is still very good. You can also go to larger systems from 30 silicon atoms to always 1,000, all the way to 1,000, you can parallel implement this thing all the way to about 1,000, 2,000 cores. Along the way, you always have up to around 10 times faster for all the system sizes. And you can do the Ehrenfest dynamics. This is the application, which is to get a chlorine ion going through a graphene with a different speed. So the chlorine ion would go down through the hull of this single layer carbon atom, which is a graphene, and you can compare the impact of time-dependent density functional theory with the Bohm-Oppenheimer dynamics. There is a fundamental difference between the energy transfer mechanism of the two things. Bohm-Oppenheimer dynamics says that the electron needs to stay at the ground state at each time step. So as the chlorine ion becomes faster and faster, the energy transfer mechanism becomes almost mechanical. Especially when it's like when you shoot a bullet through a paper with a hole, then actually when the bullet becomes very fast, the paper wouldn't do very much. And there's a little energy transfer as the initial energy becomes faster and faster. This almost goes to zero. TDDFT is completely different. It says that when there is a bullet going through this paper formed by the carbon atoms, because the length scales are so small, there will be a significant energy transfer from the kinetic energy of the chlorine ion to the potential energy of the electrons on the graphene. And therefore, as the energy gets higher and higher, there is a significant energy transfer from the kinetic energy to the potential energy, and these two things really diverge. To verify this thing, you can also look at the distribution of the energies above the Fermi surface. You may not see it. There's a dashed line indicating the Fermi surface. Below are the things corresponds to the ground state. These are the excited states. As you increase the kinetic energy, there is a significant portion in the TDDFT of the electrons that are excited above the Fermi surface. And you can again use 100 times larger time step, and which is about more than order magnitude faster on about 200 cores. Recently, so all the things what I showed before was for this so-called semi-local density functional, or so-called generalized gradient functional, GGA, generalized gradient approximation. So there is a class of functionals called hybrid functionals that are becoming increasingly widely used in the quantum chemistry and the material science community, but it is really expensive because this, if you still remember at the beginning, there's a VHXC PT. So that one is a local thing. So like the whole operator H is a differential operator. With a hybrid functional, you're mixing it with a fraction of the so-called Fock exchange operator. That one is an integral operator. So it becomes an integral differential operator. And that application of the integral part of this Fock exchange operator completely dominates the computational cost. So everything you care about is the cost of applying the Fock exchange operator. So this is, to our knowledge, for the first time, enables practical hybrid functional calculations with this is with 2,000 CPUs. So if you were using the RK4, you need to apply 400 matrix applied Fock exchange operator to 2,000 orbitals, or almost, so this is 800,000 applications, so which is extremely expensive. You have to solve 800,000 Poisson equations for each time, each unit time, which is 50 attosecond. Use the parallel transport, you dramatically reduce this to 20. Combined with a more recently developed technique called adaptively compressed exchange, we have further reduced this to about less than 6 on average per time step. So this is over a 70 times reduction that really enables the calculation with a large basis set such as plane waves. By the way, the largest example to our knowledge using the hybrid functional calculation in the literature is about 8 atoms. And not because you cannot do much larger, but this is just to get you some idea. It is really, really expensive to do this type of calculations. Last week, we submitted a paper, and so demonstrating this thing can be further significantly accelerated on Summit, which is an Oak Ridge supercomputer, which is the #1 publicly available supercomputer on the top 500 list on the late November. So we simulated this, should definitely, to our knowledge, unprecedentedly large system, which is a 1,500 silicon atoms with scale to 700 GPUs. Remarkably, this is more than 30 times faster than the best CPU implementation with a similar technique, with the 3,000 cores. And I want to say that, so this is the strong scaling, even with 30, I think with 72 GPUs, this is already 7 times faster than the best CPU implementation. With parallel transport, with RT4 will be completely on the top of the roof. As a matter of fact, it has been widely accepted that the real-time TDDFT with hybrid functionals will be thousands of times slower than the Born-Oppenheimer dynamics corresponding to using this local or semi-local exchange correlation functionals. But we managed to get a very practical time to solution, which is 1.5 hours per femtosecond. So that really enables you to do some calculations that you couldn't do before. So let me say, conclude this part, or depends on the time, maybe even this talk, that, so I talk about the parallel transport dynamics, which is the optimal gate. It sort of combines the best of both worlds. And one is, it gives you the cost with the Schrödinger dynamics by propagating wave function-like objects, but the time step can be like von Neumann dynamics, which is density matrix type of object. So we sort of want to say that we make, in this business, make implicit time integrators cool again. Or, so, and I don't know whether it's really cool again, or maybe it has never been cool in this business, and but really, we think it is effective. So it depends on the decision of the chair. I can proceed, or should I? Okay, so let me very quickly jump through the 2,000 slides I have next. Okay, I don't have time to talk about it. So let me thank the people who did the work. And so there is a brilliant student, Dong An, from math department, and third-year grad student at the math department of Berkeley. And he also, together, did the localization part. Dr. Wei Hu was previously at the Lawrence Berkeley National Lab. He's now already a professor at USTC in China in the chemistry department. And so Dr. Wei Jia, who is a postdoc in the math department of Berkeley. I'd like to thank my senior collaborators, the funding, and thank you very much for the attention.
We have time for some questions.
So, are there experimental results on benchmark problems that you can compare the results with?
Oh yeah, very good question.
What do they show?
Yeah, so TDDFT is by now, I think it's safe to say that the most popular method it's not as popular as ground state Kumsham DFT, not as dominating as ground state Kumsham DFT for ground state calculation of many-body systems, but still I think it's the most popular one because it's easy to use for this excitation things. It has known limitations such as some complicated processes such as double ionization and so on and so forth, but there are books and review articles demonstrating that when it will be good and for what kind of systems it will be good. But it can really be used to measure many things that are of interest with excitation properties. So for example, you want to understand, let's say, a color of a material, right? So what does it really mean? It basically means you want to compute the absorption spectrum. What it actually means is you apply electric field, you apply the external field that takes a particular form which is almost uniform on the macroscopic perspective. You observe the change of the electron density with respect to time, measure the difference, and do a Fourier transform, and which is what you have seen earlier. And this is only one example. The pump probe example is another very becoming more and more popular, with appearance of some very recent facilities at, for example, the SLAC at the Stanford and other places with this femtosecond ultra-fast type of facilities, and there will be more and more people doing this kind of things. But there are also many other applications as well.
Other questions?
I just want to say there's really a large community doing that. Yeah.
I have one question. So this gauge that is referred to as the parallel transport gauge, I had some intuition that it's supposed to be following the main phase of whatever's oscillating, and that kind of reduces your time variation, your time variation overall. But can you give us some intuition about what the thing that is being parallelly transported is? What is there a quantity that is, a little more connected to like a classic parallel transport idea?
They are.
Can you give us some intuition about this?
Yeah, so that's why I showed very briefly, this underlying equivalent parallel transport dynamics, which is this. So this one is, a parallel transport basically you take something, you have a propagator propagate from this something to somewhere, right? So what I'm claiming is the solution of the parallel transported orbitals exactly satisfy this thing, which is T, which is that operator, transporting the initial orbitals to this different thing, which is within the range of PT, which means that it's not just that you're rotating, you span the same space, right? So you're applying on the left, so you're changing the subspace, but still within this subspace rotation, and that is the best thing. And what you can see more intuitively is actually from this P phi dot equals 0. Geometrically, what is going on in a 1D picture, maybe you couldn't see that, but in a 1D picture, it would be like you're going like this. At the beginning, you have some psi naught, and here it is some psi t, which induces a projector, which is PT. But at each time, you can think there will be some sort of things within the tangent space. There will be something orthogonal to the tangent space, and every time you only keep the, it's hard to see that in 1D, but you only keep the part that is orthogonal to the tangent space.
So it's the actual initial condition itself.
Yeah. Yeah, that's right. To answer your question, you're transporting the initial condition.
Other questions?
I know you didn't get to localization, but I was wondering if on top of this optimization of gauge choice, that you are also use the maximally localized Wang functions to also optimize your basis representation to further reduce the computational complexity?
Oh no, that's actually a completely different problem,
No.
which is localization. You can combine those, but however, if you want to combine those, remember this is uniquely defined. So the only degrees of freedom you're going to do is the initial step. But the localization is a completely ground state problem, and I would refer to the local expert.
Could you say, is this, are there any restrictions on the classes of materials that this method would apply to? And if so, where do you see that in the
No. So there is definitely a restriction, which is how would you do for metal? But that's not the problem of this. So TDDF, to my knowledge, TDDFT for metal in the real-time case is still a research frontier, because it's very hard to discuss what is a fractionally occupied orbitals without this gauging merge. There are people doing that, but even those people who do that, they will acknowledge that there is some severe theoretical challenge going on there, although we can formally carry out the equations. So yeah, for metals, I think that would be sort of limitation, but not because of this formulation. It's rooted from a more fundamental level. And then it doesn't matter whether you're using insulator or semiconductor or some or molecules.
I want to go ahead and thank Lin again.